So in this section, we're kind of extending what we did in 9.2. So if you understand Taylor and Maclaurin polynomials, this is going to be pretty easy for you. Because all we're doing now is, instead of stopping at a finite number of terms to get a function that approximates some other function, like sine of x, e to the x, ln of x, we are going to be adding infinitely many terms. And that's why we call these series. And in that case, we get something that exactly equals the function it's representing. Okay? It exactly equals the function it's representing. So we call these power series in general. Okay? And what makes a power series? It's basically a series with an x in it. Okay? So it's pretty easy to spot. So everything that we did in 9.1 just was a function of n. And sometimes it's a function of I, j, or k. But it was a function of n. So now we're going to have series that are a function of n, but they also have x in it. So for example, this would be a Maclaurin series or a Mac series, which means it's centered at what? 0. So this would be the sum from n equals 0 to infinity of a sub n times x to the n. So the function for the expansion is n, but there is an x in it, okay? And so when we expand these out, they end up being polynomial functions, just like in the previous section. But the only difference then is, instead of stopping like at x squared and having a squiggle sign right here, we actually have an equal sign, and we go on forever. So plus dot dot dot, or plus dot dot dot, and then what we call, remember, the nth term or the rule of sequence, and then plus another dot dot dot. So this is really what we're after. All right? So these are going to now equal some function f of x. Actually, the equal sign here is always going to be an equal sign. Okay? The equal sign that's important is this one here. It doesn't any longer approximate some function f of x. It equals the function f of x. But here's the thing. It might not equal the function for all values of x. Okay? So this would be centered at 0, and you could spot that pretty easily because it's just x and x squared and x to the n. So in general, we have a Taylor series, which we can center anywhere like at c, and it kind of has the same look, but it has the x minus c squared, x minus c cubed, x minus c to the fourth. So it won't be simplified, expanded. You'll actually see x plus or minus the center. All right, so again, this is going to represent possibly some other function g of x, and it's an equal sign there, not a squiggle, okay? Maclaurin Taylor polynomials, finite terms, only an approximation. Always the same at the center, right? Always the same at the center, but an approximation everywhere else. Here we're saying it's equal to the function everywhere over a certain domain. And so that's what we're going to be interested in finding. For what values of x, then, is this polynomial function truly equal to the function it's representing? It can't always be all real numbers, because not all functions like polynomials have domains of all real numbers. So here's kind of what we're looking for. Let's say we have the function ln of x, and I'm just going to use this for illustration. The natural log of x has vertical asymptote and looks like this. So that's a transcendental function. And we looked at a Taylor polynomial in the previous section centered at 1. We can't center it at 0. So there might be a power function or a power series that is perfectly natural log of x for all values of x in a certain interval. So that function might look something like this, and then it might look something like that. So it could very well be like a quadratic, let's say, okay, something like that. Well, the polynomials domain is all real numbers, yes? This line continues to cross the vertical asymptote and go down forever. There's no way we can say that it represents the natural log of x everywhere, right? Because the natural log of x doesn't live at 0 or to the left. So what we're interested in is then, for what values of x does the series represent the function? Well, 3 things are going to happen, possibilities. First of all, they're always going to be the same at the center, just like with polynomials. So the series and the function it represents are always the same at the center. It could be for all real numbers, like sine of x, e to the x, and cosine of x. As I mentioned that in the previous section, if you go out infinitely many terms, the series equals sine of x, cosine of x, and e to the x everywhere. Or it could be the third case, which is like this. Maybe it has a radius, we call it, of 1 unit, where I can go 1 unit to the left and 1 unit to the right till like x equals 0 and x equals 2. And maybe on that interval, the function is represented perfectly by the series, and then outside of that, not so, okay? We call that the radius of convergence. The radius of convergence. It's the distance on either side of the radius that we can move left or right and have the series perfectly represent the function. Now here's the thing, endpoints are always going to be a separate issue. Okay, so if the radius of convergence in this case I would demonstrate as 1 unit, does it converge at the left endpoint of 0? No way the polynomial can represent the natural log of x at 0 because the natural log of x at 0 doesn't exist. So we're not going to be able to include 0. But maybe at 2, we'll put like a parenthesis there, maybe at 2 it could, and so I can include a bracket there. So there's another thing that we're going to be talking about that's related called interval of convergence. The interval of convergence is essentially synonymous with the domain of the series. For what values of x does the series perfectly represent the function? And in this case, with my demonstration, it would be on the interval from 0 to 2, like that, okay? We would still say the radius is 1 unit, because from the center of approximation 1, I can go 1 unit to the left to 0 and 1 unit to the right to 2. But when we test the endpoints, in this case, visually, I can't include 0, and maybe I can include 2. So we would call that the domain of the series. All right? So that's what we're doing in this section, okay? So let's look at it down here. In general, this is a summary. For a power series centered at C, exactly one of the following is true, okay? The series only converges at the center. Yikes, okay? That would be kind of a really bad way to represent a function, but that's true for all series, as it was for all polynomials. Every series and the function it's trying to represent perfectly are always exactly the same at the center. The question is there a larger interval than 0, essentially? Well, yes. It could be that the series converges for all x. That means that the interval of convergence would be negative infinity to infinity, and the domain would be all real numbers. That's going to be like sine of x, and e to the x, and cosine of x. Those are the 3 you memorize, and they converge for all real numbers, okay? Or, as I just demonstrate with the natural log function, there exists a positive radius such that the series converges on the interval from, let's write it like this, c minus r and c plus r with parentheses or brackets, okay? And the way that we write that is like this, such that the absolute value of x minus center is less than r. It converges when it's within r units. That's how you read this. The less than means it's within r units of the center. This is sometimes called tolerance form or margin of error form, like from statistics. X minus the center absolute values is within r. And then it would diverge for x minus c greater than r. This would mean outside of r units from the center. So with the natural log problem we just saw, it converged with a radius of 1 from 0 non-inclusive to 2, okay? R is called the radius of convergence of the power series. So let's talk about what the radius is. And I have it down here. But in the first one, if it only converges at the center, the radius of convergence is what? How far can we go left and right if it only converges at the center? 0. The radius of convergence would be 0. If the series converges for all x, then from the center we can deviate how far left and right? Infinitely far. And so we would say the radius is infinity. And of course, if there's a finite radius, then the radius r is just whatever r is. Okay? In the example we just saw visually with the natural log, it was 1 unit. Okay? So one of those 3 is going to be the case. So the corresponding interval, c minus r, c plus r, is called the interval of convergence. And if you notice what I did here on the endpoints, I put parentheses or brackets because we don't know if we can include it or not include it, parentheses or brackets, until we test them separately. All right, so here's some notes. To determine if the endpoints are included or not, we have to test each endpoint independently. And that's going to be a little bit of work, a little bit of effort, but I'll walk you through it. And we typically use the ratio test to determine the radius of convergence. Sometimes you can use other tests. But all the tests we learned in 9.1, they're all kind of back on the table for trying to determine where something converges. Ratio test works pretty much every time, though. All right, you ready to try it out? Let's try it out. Example 1. Based on the fact that a fourth degree Maclaurin polynomial for f of x e to the x is this, the fourth degree polynomial is equal to that, and that we say is approximately e to the x, right? Approximately. Why is it approximate, not equal? Finite number of terms, right? There's not infinitely many terms. Finite number of terms, it only approximates it. It says to find the nth term, then find the radius and interval of convergence for the representative power series. Okay, so here's the deal. Start way over here on the left. I know then that e to the x is not approximated by, but equals the infinite series, 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the fourth over 4 factorial. Plus, instead of stopping there, plus dot, dot, dot. Now, if you stop there, that's fine. The dot, dot, dot shows that it's infinite. But what we're really after is we're after the nth term, because we need the nth term in order to do any of our tests, okay? So can anyone see the pattern there in terms of x and n? X to the nth over n factorial. Perfect. Plus dot, dot, dot. Okay? So that's equal to e to the x for some values of x. We're going to figure out what values of x it's equal to. So here's the expanded version of the series. Let's write it equivalently as a condensed version, which is really what we want. That's equivalent to sigma from n equals something to infinity of x to the n over n factorial. Now here's probably one of the most important parts when you're dealing with series as opposed to sequences. For sequences, the first term is always a sub 1. It always, always, always corresponds with n equals 1, because you're counting first term, second term, third term. But that's not so with series, because series, we can start with n equals any number 0 or greater, 0, 1, 2, 3, 4, 5. We don't have to always start at 1. The most important thing then is when you capture the rule of sequence, you need to give your starting value of n the correct value so that when you actually plug it in, you get the actual first term that's showing. So is that 1? If I plugged in a 1 for n, does that give me my first term that I listed? No. When I plug in a 1, I get x to the first over 1, which is actually the second term. Yikes, okay? So I need to actually start at what? If I started at 0, that would work. There you go, because x to the 0 is 1, and 0 factorial is 1, and 1 divided by 1 is 1. So check that every time. When you write the rule of sequence and you can condense it down, check your starting value of n. Okay? So I want to figure out what the interval of convergence is. What are the values of x that make this a true statement? Okay? We would call this an identity if you want to think about it that way. Right? Remember in pre-cal we did trig identities? This would be also an identity, a polynomial identity. We could interchange one perfectly with the other for certain values of x. All right, so here's how we do it. We're going to do the ratio test on the rule of sequence. So remember, the ratio test is the limit as n goes to infinity of the absolute value. It's a test for absolute convergence. It's the n plus first term, so that's x to the n plus 1 over n plus 1 factorial. And again, that works great here because we have factorials. And then instead of dividing by the nth term, I'll go ahead and multiply by the reciprocal. That's n factorial over x to the n. And now the fun part, my favorite part of the ratio test, simplifying all that stuff. You have one more x factor in the top, so it is just x. And then in the bottom, n plus 1 factorial is n plus 1 times n factorial, and the n factorials divide out. So it ends up being x over n plus 1. Now, if you need to show more steps, go ahead and write the top as x to the n times x times n factorial, and the bottom write n plus 1 factorial as n plus 1 times n factorial, and then divide things out. So at this point, do whatever you need to simplify it from here to here. Okay, so now we're evaluating the limit. And remember, the variable for the limit is n, not x. So at this point, we're essentially treating x as a constant. Okay? We're treating x as a constant. Yeah, there it is. Constant. There we go. So what would be the limit, then, of a constant over n plus 1 as n goes to infinity? It would be 0, right? In other words, regardless of what x is, 10 over infinity, 100 over infinity, 1,000,000 over infinity, negative 1,000,000 over infinity, because it's absolute value, it's always going to go to what? This goes to 0. And remember, by the ratio test, it'll converge if that's less than 1. Is 0 less than 1? It is. So now we have to answer the question. It doesn't matter what x is. It will converge for all values of x. So the radius of convergence is what? Is infinity. Yep. And the interval of convergence, also known as the domain, is what? All real numbers, or if they ask you for the interval of convergence, just write it as an interval. Negative infinity to infinity. Or you could just say the domain of the series is all real numbers. So essentially what we proved is that the polynomial of infinitely many terms perfectly approximates e to the x for all values of x on the number line. And that's the same as it is for sine and cosine. But of course that can't be true for all functions, as we saw with the natural log function. Okay, now we don't really need to come back and test the endpoints here on the interval, because infinity and negative infinity are not really endpoints, okay? So this one converges for all values of x. That's another way to say it. Let's say that up here. This converges for all x in the set of real numbers. All right? That's another way to say it. All right, not so bad, right? Kind of fun? Sweet. All right, so often we're going to be dealing with power series that represent unknown functions. We're not going to like have a power series and say, oh, that's like natural log of x squared minus sine of x or something like that. We won't know the equation of the function they're representing. But we can still determine for what values of x it represents that unknown function, that non-recognizable function, I should say. And then you'll be able to sketch it on that interval and see what the graph might look like approximately for a finite number of terms, okay? So we're not going to have the satisfaction of knowing, oh, that's the same as e to the x. It's just going to represent some unknown function. Let's try that on example 2. Find the radius of convergence and the interval of convergence. Be sure to test the endpoints. So this makes a fantastic free response question. Finding the radius of convergence is one thing. Finding the interval of convergence is going to require a little bit more work because we have to test endpoints. All right. First thing you're going to notice is that it's a power series. Why? How do I know it's a power series? It's got x, right? So it's a power series. What's the center? That's probably the most important thing. 1? 5? Negative 5? It would be positive because remember up here in the standard form, it's x minus c. So just like with standard transformation form, it's x minus the center. So the center on this one is actually 5. Okay? So here's what we know before we even start. We know that this series for sure converges at x equals 5. We know that already, okay? Because that's true of every power series. The series and the function it represents ultimately have the exact same function value at the center. But are there more values of x for which that thing represents it? We don't know. So notice it is an alternating series, and the ratio test is a test for absolute convergence. So we can dismiss that when we do the test. So let's do the test. So I'll go ahead and write the ratio test, treating this as a free response, okay? Navigating through the work. Ratio test. The limit as n goes to infinity, absolute values, x minus 5 to the n plus first, all over the two quantities, n plus 1 times 2 to the n plus 1. And then instead of dividing by the nth term, I'll multiply by the reciprocal. And there's the setup, okay? Times the reciprocal. There's the setup. And then it gets fun. Then it gets fun because now you get to algebraically simplify all that. So let's see what happens here. The x minus 5s, you end up with 1x minus 5 in the top more than the bottom. So that's done. The 2 to the n's, you have an extra 2 in the bottom than the top, so that divides out. And then you're just left with an n in the top and a quantity n plus 1 in the bottom. All right, so remember, n, again, is our variable. And so x, or in this case, x minus 5, we're treating as a constant. And of course, 2 we're treating as a constant, because it is. And so I really have n to the first over n to the first, as n goes to infinity. That's leading coefficient over leading coefficient, isn't it? So that's going to be, the leading coefficient of n on the top is the quantity x minus 5. So we're just left with x minus 5 all over 2. So in this case, it didn't go straight to 0. It went to x minus 5 over 2. That will only converge if it's what? Less than 1, okay? So if there's still a variable left, you're going to force it. You're going to force it to be less than 1. All right, now here's your target. This is your goal. As I said way up here, referring back to this, it converges when this is true. X minus the center is less than the radius. So that's our goal. So specifically in this case, with the 5 as the center, our goal is to get it into this form. X minus 5 is less than some number r. That's our goal. Well, all I have to do that is multiply both sides by 2, right? And because it's positive 2, we take the absolute value. I don't have to flip the inequality. So it's less than 1 times 2 is 2. And there it is. You kind of have all the information you need. This series will converge as long as you are within, that's how we read it, within 2 units of the center 5. Okay? So the radius of convergence is what? 2, yeah. The radius of convergence is 2. That number that you get less than or equal to, that is the radius of convergence. Okay, so if this were a multiple choice question, it'd be done. The radius of convergence is 2, game over. But now for the interval of convergence, what, we're in here until 12:15? I have to do that after lunch. Here's what we know. Draw a little number line. I like to draw the number line. I know the center is 5, yes? That means that we're able to go plus 2 to the right and minus 2 to the left, which puts us at where? 5 minus 2 is 3, and 5 plus 2 is 7. So I know that the interval of convergence is going to be from 3 to 7, but I don't know if I can include the endpoints or not. Like with the natural law. Looked like visually we could not include the left, but we could include the right. So we're going to have to test those values. All right, so make a new column here. We're going to have to test the endpoints of x equals 3 and x equals 7 to see if they get brackets or parentheses. So let's go ahead and just set up the first one. If we do x equals 3, again, you want to label your intention because you're doing more than one thing. Here's how you test it. All you're going to do is you're going to plug that back into the original series for x. And so that'll look like this. It'll be the sum from n equals 1 to infinity of negative 1 to the n plus 1 times, if you plug in a 3 for x, 3 minus 5 is negative 2 to the n all over n times 2 to the n. And now, after lunch, we'll do this. Now it turns into a 9.1 problem. Notice now there is no x in it. Now any test from 9.1, parting C, is on the table as a way to determine if this thing converges or diverges, okay? And we will do that after lunch. So have a good lunch.